Okay, tonight's presentation is the antenna analyzer. And as you can, well, you can't see it. The slide's not up yet, but you will soon. Applications in amateur radio. And this presentation tonight is being given by Ron, WA6YOU, and George, WB5OYP. Did I get that right? You have a hard call sign to remember. You should, you know. Anyway, you probably will not find two more capable and intelligent folks in the club with respect to antennas, their theory and operation. So have at it tonight with these guys. They've got a lot of great information to put out, and I'll let them introduce themselves in more detail. And I'll let you talk about whether you want to have questions during or after. So over to you, Ron. Thank you.
Okay. Yeah, thanks, Mike. All right. Ron Payne and George Lemaster. We did this 3 years ago. It's been 3 years already. He came over on Wednesday and we totally redid it. So hope this will answer any questions that came about 3 years ago. So a little bit on me. I was licensed in Livermore, California, 1962. Been a ham a long time. Got my extra in 79 when you had to go to the FCC. I have a first-class phone with ship's radar. I know a lot of people in here have a first phone back when it was a real first phone. I was a radioman first class SS in the United States Submarine Service. I rode 2 nuclear submarines, got out in 1970. And joined the Foreign Service, went overseas to Bangkok on my first tour, could not ham. My next tour in Manila, I was able to get a license. Went to Beirut in 1975, took 6 months, but I got a license in Beirut. So that was some really, really good ham radio operations. New Delhi, India for 4 years, operated there. Did a de-expedition to Kathmandu, Nepal in 1982. 2 Japanese and 4 Americans. We went up and put Nepal on the air for 2 weeks. Had a license in Frankfurt, Germany, but didn't use it one single time. I had a license at my uncle's house in Hampstead, London, and again, didn't use that ever either. Did a de-expedition to Gaborone, Botswana, 1988, 2 weeks in the Kalahari Desert. A lot of fun. And I was on the air during Black Hawk Down in Mogadishu in 1993, then went back in 94. And I've had a lot of special event stations, worked with people on that. Guys, tonight, what we're going to do is George is going to give you the basis. He's going to give you the background, especially, this is geared especially for the new people here. Background on a little RF, what you need to know, what your antenna looks like to your radio, what the analyzer sees, and what the antenna sees, and what the radio sees. So I'm going to let George take care of that. And then I'll go over that wonderful subject called SWR. I'm going to make it as easy as I can. And then I'm going to go over each one of these pieces of equipment, and we will use one to check the antennas. One of the meetings, I think the last meeting I spoke to you, we built the 4-element Yagi. You guys remember that? Built the 4-element Yagi on a pasteboard. Great, great piece. And then back in November, we did the quarter wave ground plane, and that works like $1 million too. So we'll be using all these tonight, along with some of the VSWR checkers. So with that in mind, George, I'm going to let you take over on the half-wave dipole.
Right.
This is the next slide. Down.
Okay, thanks. George, WB5OYP. Not too illustrious career, but I was licensed in 1958. I was 11. I had no idea what I was doing, hooking an antenna up to a transmitter, but somehow I made it work. And I think Mike had a good idea. I think one of the things we might want to think about is maybe at field day or someplace here, have the opportunity to just string up some antennas and some coax and hook it up and let people try these things so that when they get home and want to do it, they can make that all work. So we'll talk just a minute. Ron made these wonderful slides, and we'll talk about it a little bit. Let's just put them all up here. This is what everybody talks about as a dipole antenna. I know I'm preaching to the choir to most of the audience here, but if you make a wire a half wavelength long like that, you can make it resonate in a ham band. You can drive it in the middle like it's shown here, or you can drive it an end, as Ron did on his let's see, is there one more here with the impedance? Yeah. Oh. Yeah. So he's drawn here the impedance. If you feed it in the middle, you're looking at a low impedance. When these antennas are hooked up somewhere off the ground that you would probably use them, the driving point impedance of that somewhere matches a 50 ohm coax. It's somewhere maybe, let's say, between 50 and 70 ohms, something like that. And it's everybody drives it as a 50 ohm cable. It just seems to be the norm. It varies as you raise and lower the antenna above ground, but this gets you in the ballpark. This diagram shows that the current stops out here at the ends of these wires, and the reason is because there's no place for the electrons to go once again, so they have to go back down the way they came in. And so when you apply an alternating current to this from your transmitter on some ham band, you get an oscillating current on this half-wave dipole, and we'll talk just a little bit more. It magically sends signals out into space. Pretty cool. So Ron says, what's the magic? Well, there's not too, there is some magic, to be honest with. This is kind of a really interesting thing in the world, in the universe, of why in the world does this thing radiate? And it comes about because as we drive a current into this wire along here, getting mixed up, as you drive a current into this thing, you create a magnetic field around the wire and you create an electric field between the wires. And due to some magic, really, the fields that are induced in that will expand out into space, and they just keep going. Just like you can see the light from some star far away, and the receptor in our eye that's receiving that electromagnetic radiation, which is light, can travel through space long distances. So the trick, though, on hooking this up in your ham rig to an extent is getting these things tuned so that what the radio sees is a resistive load. I'm sure most of you have had some background electricity. You know a little about a reactance, and that if you want to dissipate power in something, you have to drive it into a resistive load. And so the antenna, as you drive it with its, just by its nature as it is, it's not really very resistive unless you do some tricks. So the magic is that if you make these arms the right length, and Don has a slider here, make something to a certain length, and if you measure this for the right length, it will actually resonate at a certain radio frequency. And so what's going on there? Well, what happens is, I'm going to go to the next slide. The arms of that antenna, they're wire. They actually have inductance. And if you think of it, it's really a series of little inductors all in a row. And then there's capacitance. So capacitance is just two conductors separated by an insulator. In this case, the insulator is air. So there's an electric field between points along this wire as charges move up and down the wire. And there's inductance in the arms or the wires that you used. The trick is when you're building one of these antennas is to make those inductance and capacitances such that they happen to cancel in the inductive reactance and the capacitive reactance at the frequency that you want, and null out the capacity and inductive effects at that point. And that leaves you with just the resistance in the circuit. The next slide shows that. And you can think of these, this is what we call just lumped elements. It's the same idea, but we've added a couple of resistors in the path. We'll talk about those. And we've added the fact that there's an alternating current generator that we call our radio transmitter. And we have to add something called a transmission line. We'd like to put the antenna up in the air somewhere outside our house and have the radio inside, and we have to get the signal out to the antenna. So the challenge becomes, what does the radio see? The radios of today are designed to see 50 ohm resistor. That's what the designer really would like it to have connected on the output. That solves a lot of problems for him. He doesn't have to worry too much about what else you're hooking. He did his job. If you hook 50 ohms onto it, you'll get the power out of it that you wanted. But in the real world, when you hook a transmission line to that end, to that transmitter's output, it probably doesn't look like 50 ohm right off the bat. We have to adjust some things or add some equipment to make it so that the radio sees that 50 ohm load. Most of the radios today or I should say in times gone by, had an antenna matching network of sorts built into the radio, particularly back in the tube days. And so you could hook up almost anything. Like when I started out, you could hook almost anything up to the transmitter, and the transmitter would load into it because it had enough knobs on it that allowed you to adjust for the antenna wire that you connected. But today they don't give you so much in that area, so you have to buy something called an antenna tuner or have one that's built into the radio for you to match whatever impedance the antenna circuit really is. So here we're representing this as the two lumped elements, the capacitance of the antenna and the inductance of the capacitance. There's one more resistor down here. This RO, or as Ron calls it, the ohmic loss, that's just the resistance of the wire that made your antenna. Like if you've got an 80-meter dipole and it's 100 feet long of number 12 wire, it's got a certain resistance, maybe 1 or 2 ohms DC resistance, and that factors in. So you waste a little power in that, but that's not the big thing. The other part of it is called the radiation resistance. And this resistor is actually fictitious, but when you hook the transmitter up to this antenna, some of the energy gets lost, and it gets lost because it got radiated out into space. And so the current that went through that fictitious resistor, and it's just current squared times the resistance, which is E equals I squared R, that's the amount of power that the antenna radiates. And in a lot of antennas, this ratio of this radiation resistance to the loss resistance is really going to determine the efficiency of the antenna. Most of the antennas we're going to build for HF, you don't worry about that because this is so low, and this is something reasonable, you know, on the order of, in the case of that dipole, maybe on the order of 70 ohms, 30 to 70 ohms, somewhere in there. So most of your power is going to get radiated by that antenna. Like I said, it just gets dissipated out into space. It's a wonderful thing, and that's how we can talk and how we can receive things. So the trick is here to null this out and understand over here when you're at your radio what's going on as you do that. So Ron's got some antenna analyzers he'll show you in a minute. The idea is to hook something up at your end of your coax and see what the antenna is. So in this case, he's representing here that you're going to see the whole circuit. The coax cable, maybe that's 100 feet of wire, coax cable, and whatever your antenna is that you strung up. And in space, it would be one thing. But in your backyard, where it's dangled between your house and the trees, there's fields go all over the place. You can't see where they go like they were in that earlier diagram. But the idea is that you want to be able to null this out. And so you can do this by playing with the length of the antenna, the arms, bring them shorter or longer, and create that resonance effect. And you'd like to see that on the antenna analyzer. What you're really doing in this case is getting the antenna by playing, let's say, with the length of the antenna so that it represents something close to that 50 ohms resistive load at this end of the coax. It's a combination of things you're looking at, includes all of this, is what the analyzer is going to see, but that's what the radio is going to see. So in a lot of cases, that will get you where you need to be. This point is that the antenna analyzer, when you're using in a case like this, like something I didn't really mention, I really should say now, is that the coax that you use, you go down to the ham radio outlet and buy 50 feet of coax that says 50 ohms on it. If you put the analyzer on it and said, tell me if this coax looks like 50 ohms resistive, looking into the coax, that's true if the end of the coax is terminated in 50 ohms resistive. If it isn't, it's going to read something else. The transmission line will act actually as a transformer and transform whatever impedance, in other words, resistance with some reactance at whatever the end of it is, and that will reflect back to the input. And that holds for the case when you have an antenna on it. If the antenna feed point here is not exactly 50 ohms resistive, then this 50 ohm coax is going to read something else over here at the end. It's not necessarily what's here. It'll read something that depends on the length of that coax. So you're looking at the combination of the coax and the whatever the impedance is here, kind of mixing together to give you a value over here. Now, that's why he says it may or may not be equal. And trying to make this exactly 50 ohms resistive, well, good luck on that. That's like balancing something on the edge of a knife. It's possible, but usually we don't have that. We can get it in the ballpark. We can get it reasonable, good enough to operate, but there's other ways to fix the problem. But the point is that it isn't exactly on there. So Ron's pointing out here is if you have the antennas too long, there's more inductance than capacitance. It's going to look inductive. If it's too short, then it's going to look capacitive. But how could you fix that? Well, one way is to add some inductance in there. They're kind of, one's the antidote for the other, so you can get it to cancel out. But in either case, it's a series circuit. And again, what the radio sees through the coax is something out here, and you're trying to trim this and look through this coax to see, to make it reasonable for your radio. If the antenna is resonant, as we talked about, in other words, the inductive capacitance and the capacitive reactance is equal, then it will resonate. But that occurs at one frequency. That's one point if you cross the two graphs that they cancel. Otherwise, it's going to look inductive or capacitive just as any LC circuit would, any inductor and capacitance circuit would look. So again, here we're seeing that the antenna would be, you would see whatever the radiation resistance is and the loss, you've nulled out the reactance. And let's suppose that that happens to be close to 50 ohms, then everything's good. Your radio would be operating at a reasonable speed. Now, usually, we're not that lucky. And what we're saying here is that you'd like to measure it, but the best way to measure is right up at the antenna itself. And that's usually not real convenient. So there's a few ways you can approach that. One, and this is probably for another day, we'll talk about how to use something that Ron will show you called a vector network analyzer. And what it does, it has the capability of nulling out that piece of coax. You can do a little procedure with this analyzer and effectively save the characteristics of that transmission line, whatever its length is at the frequency you're trying to operate it at. And it puts that into the analyzer. And then when you look at the signal or the results of the impedance that the analyzer is giving you, it's doing it by nulling out the feed line, if you will, so that you can get a good idea of what's exactly going on at the end of the feed line. There's some other ways you can do it. There's something called transmission line for Windows that ARRL puts out. It's a program you can put in the length of the coax, the type of the coax, the frequency you're operating on. And if you know all those parameters, you can then say, well, this coax is X fraction of a wavelength long or whatever it is, 100 feet, let's say, and you can get a good, reasonable approximation of what the antenna impedance is looking at the end. And it's done by computation in that program. There are some other ways you can do it, but Ron will get into that. The idea here is that with these analyzers he has, you can get a good first order of what's going on with your antenna, but think of it as that whole system, the coax and the antenna. So as you're adjusting it, just keep those factors in mind. Ron?
All right. Thank you very much. I appreciate that. Good. What I want to say first is that if this was 1972, 1978, we wouldn't even be here because who cared? We all had vacuum tube radios. They all had a pi net. Peak, dip, peak, dip. My first dipole I put up, 1962. My dad and I threw up a 40-meter dipole in the trees. I went inside my DX20 and peaked the grid and dipped the plate and got Los Angeles. And I say, hey, Dad, it's working. The SWR, what the hell's that? I don't know what that is. Never heard of it. I never bought an antenna tuner till I bought my first solid-state radio, which was 1981. I bought an ICOM 730 in Japan. At the antenna. Yeah, I'm not going to climb. I don't do ladders anymore. I think most of us in here with gray hair, we don't do ladders anymore. But if you have a VNA, you can work around the loss in the cable. The other thing that George and I want to stress here is that when you look, what your radio sees or what the analyzer sees is the coax connector and the coax connector up at the antenna and the antenna and all the dielectrics around the antenna. And we can really just worry and fret and everything. And the best thing to do is just put it up and go have fun. I hear so much of this thing about SWR. And this generation, this new generation of hams has become obsessed with SWR. I have a book at home by Maxwell. It's an inch thick, and that's all it is SWR. Can you imagine? I guess what George and I are saying, put up an antenna and have fun. Okay. All right. What is SWR? Now, I've taken this whole inch book and I've made it into 4 sentences. On a transmission line, coax, the ratio of the maximum voltage to the minimum voltage is called VSWR. Well, we won't use the term VSWR tonight. We'll just use the term SWR. You never say my VSWR is 1, my SWR is 2, mine is 3. There's no such thing. It's 3 to 1, it's 4 to 1, it's 1 to 1, it's 1.25 to 1. It's always a ratio, the best being 1.0 to 1. You can only have 1 to 1 when the transmission line is terminated in a pure resistance of the same ohmic value as the transmission line, just like George says. You can only have 1 to 1 when the antenna is 50 ohms, coax is 50 ohms, your connectors are 50 ohms, everybody's happy. You think any of us in this room have that at home? No, not a one of us. But we're close. But we're close, right? Okay. If the load contains reactance, and I can give you just 2 simple reasons why it would contain reactance. 1, it's too long. 2, it's too short. There's 2 real easy reasons. Or if the load impedance is not the same as the characteristic impedance of the line. You mean feeding a 50 to 75 ohm antenna with a 100 ohm coax. How about that? Can you do that? I'm sure that's been done. I had a student who actually fed his ham radio shack, the cable guy, gave him some RG59. He ran his whole station with it. Yeah, it works fine. But you might want to divide 75 into 50, and you'll get 1.5. So the best VSWR he'll ever get is 1.5 to 1. Does it work? Yeah, it works fine. The interference of the forward wave and the reflected wave creates standing waves. Now, I know this is all gobbledygook to some people, but we are striving for something under 2 to 1, okay? I know the government standard when I was in the government was 3 to 1. Anything better than 3 to 1, hey, you're on the air, let's go home. Implications, why do we even care? This is 2023, why do we care? All of your solid state radios today have crowbar circuits, which we call foldbacks. I have a ICOM 756 Pro 3. When it hits 2-to-1, and I don't mean 1.99, I mean 2-to-1, it crowbars back to 50% power. Okay? My TS-820 with the vacuum tubes never did. It didn't care. 2-to-1, maybe my plates will glow a little red, but I'll go all day for you. So, everything has crowbars, the foldback circuits. I have a walkie-talkie that I bought in 1960-something. It's a Tempo. No protection. Took the antenna off, and if you keyed it, you'd hear, you just blew the power transistors out. True story. Number 2, increased feed line loss. When you have your tuner, your radio, the antenna, all radio waves are eventually re-radiated by the antenna minus the loss of the cable. Okay? And the last one, you can sure damage a radio if you don't have foldback. But everything has foldback today. I think every single radio that is solid state has a foldback circuit in it. So that brings me to the next thing, couplers. Is everybody using an antenna coupler, an HF, or an antenna tuner? I think everybody is, right? Yeah, me too. We call them a lot of different things. Antenna matching unit, impedance matching unit, matchbox, matching network, transmatch, antenna match, antenna tuning unit. And my question there is, do we need one? Yeah, I think we all do. I know I sure do at home. I'm running a trapped dipole for 20 and 40. That's all I run. Okay. Back in the day, we used to differentiate between the two terms, coupler and tuner. Two different things. So here's your ICOM 7300, which 98% of you have, and it has a tuner inside of it. And if you read the manual, it's good for up to 3-to-1. It'll match 3-to-1. In other words, it's for tuning your 40-meter antenna up and down the band, just the band. Divide 50 into 150, you get 3-to-1. So you cut your antenna maybe for 7150, and it'll work at 7300, and it'll work down at 7001. Okay? So a tuner located in the station or in the radio is good for excursions up and down a band. Don't put up an 80-meter dipole and try to tune it on 40 with your internal tuner. It'll go right into the stops. Back in the day, we used to call the tuner coupler that went at the antenna, we would call that a coupler. The coupler, look at that. That's an MFJ there. That thing will tune a paperclip. 1,600 ohms. That's why you can take that coupler, mount it on the ground, and put up a 47-foot vertical with some radials and run the entire spectrum. Okay? 160 through 10 meters with one antenna. That's the difference between coupler located at the antenna and tuner located in your house. Let's talk about some of the equipment here. And I'm going way back here to 1953. Anybody in here have a bird? I know you guys can see these at the Hamfest. These are always for sale. They're a great old rig. But please keep in mind, this is not an antenna analyzer. This is an RF power meter, and it measures only two things. Let me buzz in all the rest here. All right. Measures forward power, and when you turn the directional coupler, it measures reverse power. You could pull the formula out of your calculator to calculate the SWR, but I have a chart on the back here that I super glued, made by Bird, and I can get the exact SWR. Now, this thing is only 5% accurate at full scale. The body itself is $350. That's not what's expensive. What's expensive now are the copper beryllium directional couplers. And they make these for 100 milliwatts for full scale reading, all the way up to 10,000 watts you can put in here for full scale reading. 450 kilohertz all the way to 2.7 gigs. And please remember, this is 50 ohms. This is 50 ohms, period. Little place on the side to carry ones for a trip, and I have VHF, UHF, and HF. And the other nice thing about this is it is built like a battleship. I've dropped these on the concrete. I dropped it in the sand, everywhere. It's a great little rig. And again, I have a case, and in the case is thousands of dollars worth of directional couplers. One here says 1 watt full scale, 150 to 250 megs, 2.5 watt full scale, 400 to 850 megs. So just another one of those things that you can find that has not changed since 1953. Still making them. MFJ. Anybody have one of these? Oh, okay. You know, doesn't cost much. This one covers all the way up to 70 centimeters. Run you about $310. You notice on the bottom of these guys, I'm saying don't transmit into those. You think I've ever had a student hook up a walkie-talkie and put it right into one of these and key it up? Yeah. And burn it out? Yeah, it's happened. All right. This is my favorite of all. This is the Comet. It's one of my favorites. It's got both the TFT display and analog. Very hardy. The batteries seem to last forever. Run you about $430, $440. I do have a case for it that you can wear on the belt. And here's the thing. Unlike the VNA and some other ones I have here, I can teach somebody to use this in about 5 minutes. I can teach somebody in the field, here's what you're looking for, here's how you do it. That's the reason I really like this one. So we'll come back to that one. Now, there's one for you. I got this in 2007. Let's see here. I got this in 2007, $1,400. The original VNA. This is the original VNA, but it's for HF only. Time Wave. You guys might have heard of Time Wave. They make some really hot commercial gear. The only thing I don't like about this, it really eats the batteries. So I don't really like taking this into the field. Takes 13 dBm, shoves it into your antenna and reads back. And if you want a Smith chart, you got it. You want SWR, you got it. I mean, you want magnitude of impedance, it's all here. It's a real, very nice piece. And Lee, didn't you say there's one of those in the lockup that you guys tried to sell? Tried to sell it. Nobody interested. Guys, this is $1,400 in 2007. Put new batteries in it. Buy a charger. Got yourself a real nice piece there. All right, and then there's the CSI Nano VNA, which is sweeping the market these days. I just bought mine 5 days ago. Thank you, Mike. I appreciate that. This thing does everything, and you and both of you gave a briefing on this. How long ago was that? About a year? We might want to visit that again. Because I'll tell you what, guys, this thing, $88? Really? I got it on Amazon. Works like $1 million, but this is probably something I wouldn't take into the field for the work that I do. Too many moving parts, too many little things to lose. Not when I can just grab this and a couple adapters and I'm gone. And I don't need the accuracy that this has. I don't need that. Guys, to wrap it up, we're way over. I wanted to take this antenna here that we made at one of the meetings, I think in Dean's garage, and we're going to hook it up here. It's at about 8 feet of coax. And this is cut for 450 megs. Sorry, 446 megs. And I have a SWR of 1.3 to 1. And can you see that? So, guys, that's how easy this was to set up. You just dial in the band, and it has a cross needle on it, and you tune for minimum SWR. And I've got about 444.4. Okay, I'll stand still. All right. Now, George had a great idea. One thing we're doing here, guys, we're measuring the connector, the adapter, the coax, the connector, and the antenna. So let's add something into the equation. I got another 8 feet of coax here. What do you think that'll do? Any idea? What do you think it'll do? It'll probably. So you come in the house and you go, oh my God, 1.0 to 1. It got better. Yeah, there you go. What we have here, guys, is RG58, which thou shalt never use on 450 megs, right? This 8-foot piece is losing 1 dB. So what I've done in here actually is put a 1 dB attenuator in the system. Now, let's back up. I have a neighbor. 20 years ago, I have a neighbor. He's SK now. He was having trouble with his HF dipole, and he told me, heck, Ron, my SWR is better now than it was 25 years ago. So I remember cutting into the cable, and the braid had turned green, and the dielectric had turned brown, and the solder connections on it, well, everything was a joke. But he says, I told him, you want me to replace everything? And he said, no, I'm not going to last that long. And he didn't. So anyway, guys, good demo, George. I appreciate that. And all we did is add 8 feet. Okay. The next one I want to check for you is this one. You guys remember this? We built in the last meeting, and I'm going to measure this, quote, at the antenna. Let's measure this at the antenna. Ooh-wee. All right. About 1.4 to 1, Jasek. About 1.4 to 1. Everybody see that? Yeah. And about 80 ohms. By the way, 1.4 to 1. You still use this? Sure. Worked just great. Okay, let's see if we can improve things with this. And you guys see that I changed everything to BNC connectors last night just so I wouldn't be standing here screwing stuff in all the time. Oh, good. 1.4 to 1, 50 ohms. All right. And last but not least, has anybody built one of these? Boy, these really are something. If you've ever been into direction finding, we call these DF antennas. We should probably have a workshop on this someday, because this thing really works well. And this is 2 meters, so we're going to switch connectors here. And I'll go to 2 meters. And let's see what we got here. Okay. Not too good. Okay, 1.4 to 1 at 1.4 to 1 at 148 megs. Okay. 147. Actually, at 147, it's 1.5, pretty much across the whole band. But it's good. Bottom line, guys, this is good for the whole 2 meter band. Okay. All right. Now, I was going to have somebody make an antenna. Guys, this is one of those collapsible, good all the way from 150 megs to 460 megs, whatever you want. I use this in class. So I want to make one for 222 megahertz. Okay? So guys, let's just see if we can make it right here and see if we can get it to work. And these are just super for demo. And the company that made these, he no longer makes it for hams. He only makes it for government. Okay, 220 megs, huh? Let's see what we got here. Okay, 221.9. I have 1.2 to 1 VSWR. So we just made an antenna real quick. All right, got it? All right, guys. Any questions at all about anything? Yeah, Leon.
Yeah, I got one. What if you use a coupler and the wires is really short compared to friction? What's it cost you? Do you lose a lot of energy out when that happens, or is the impedance matching? Does most of the power go out anyway?
Most goes out.
You're talking about you're running a very short antenna for the band.
Yeah.
Yeah.
Radiation resistance goes down, so it's not as efficient, and losses can beat you up, but all the power has to go in there.
Well, I know it goes in. Does something heat up then?
And one way you can consider it is it's again that loss ratio of the radiation resistance to whatever the loss resistance. So the radiation resistance on a really short antenna for a band is going to be much lower than what you would expected if it was more appropriate. So that will is where some of the energy is going, is just wasted in the loss resistance of it. But in reality, if you didn't have any losses, the antenna does not have to be resonant, as long as you can match the feed line into it so that it looks resistive. But as you go down in length on the antenna, radiation resistance goes down at a given wavelength. And so then that ratio comes into play that we talked about earlier to the ohmic versus the radiation resistor.
Yeah, I just want to add one quick comment. as George says, do you have to have the coupler at the antenna? And the answer is no. But the trick is make sure that you're running very, very low loss transmission line.
Right.
And I do that. But what I'm running is I have like 450 ohm open wire feeder, and that has very, very low loss. So even though I have a high VSWR, since the inherent loss is very, very low, I can afford to put my, if you will, coupler at the station end of my transmission line, because I'm not using 50 ohm coax. I have something that, has, I don't know, almost 100 times less loss than coax. Definitely the most efficient way to get it is to put your coupler at the antenna.
Would you recommend that you do anything about your expensive antenna analyzer to protect the connectors so they don't wear out from constant use in and out?
I love that. Normally, these come with an N and a PL259, and the problem is on and off and on and off and on and off and on and off, let alone that VNA that's got those stinking little SMA connectors on it. Every time you put it on and take it off, put it on, take it off, you're wearing that center pin out. Like Mike said, what I would buy for this is a SO239 to SO239, put it on there, and this one a type N female to a type N female. They make them, put it on there to save your machine. Thank you, Mike. Appreciate it. Okay, thanks, guys. This is my third one in 6 months, Mike, and I'm all out. I'm sorry.
Okay, that's good. Thank you, Ron, very much. Yeah. Thank you, Ron and George. It was excellent.
Well, it worked at home, and it's not working here. Thank you. Jeez. What am I drinking here? Huh? Thank you. Oh, my God. One of those nights, Jasek.